Hey, welcome everybody to 8.1 Exponential Growth. Just so you know, in Chapter 8 we're going to be talking about exponential equations and also about the inverse of exponential equations, which are logs. So we're going to be spending some time graphing these, and then we're going to spend time solving them at the end of the chapter. Today our goals are to graph exponential growth equations and then also to use exponential growth equations in real-world problems, such as like, if I have $1,000 in an account, how much money am I going to have after 10 years at 8% interest? I'll talk more about that later. Alright, so an exponential function, it looks like this. Y equals a times b to the x. That's the general format. And today we're going to be talking about when the b value is greater than 1. If the b value is greater than 1, that's what gives us growth. Alright, just to kind of show you what the parent function, or just kind of like a general function for exponential growth looks like, we're going to plot a bunch of points, but when we actually graph later, we're not going to plot as many. So just to start off with, this is an example actually, not a parent function. I'm going to have f of x equal to 2 to the x power. Remember, f of x is just a fancy way of saying y, so that doesn't change anything. Here's what we're going to do. To make our graph, we're going to create a table of values. I already have some x values chosen for us. So we're going to go through and fill in the x value to find y. So remember, when I have a negative exponent, it turns into 1 over 2 cubed, which is 8. And so what I'm going to do here is just go ahead and fill in this chart. If you want to, just pause and try it on your own first. Just every time, remember, a negative exponent equals 1 over that. So that's where I'm getting some fractions here. Alright, I'm going to keep going. 2 cubed is 8. Alright, and then I'm going to graph the points I have. So it's kind of tricky. Just do the best you can when I get to these really, really small numbers. But I got negative 3 comma 1/8. Again, just do the best you can. Negative 2 to 1/4. Negative 1 to 1/2. 0 to 1. 1, 2. 2, 4. And 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so here is what an exponential growth equation looks like. Now, the two easiest points to find on this are always the y-intercept and then the point where x is 1. So when we make our graphs later, we're just going to graph those 2 points and then draw in the general shape. Two things I want to point out. First, the domain and range. So if you look at this, if you think about the domain, that is the x values again. Think left to right, x values. Okay, if I made the world's largest graph here, all x values would be used. So my x values are all real numbers. And now for the range, you can see, when I look in the y direction, you can see that all of the values I've got so far are above 0. So we just kind of have to ask ourselves, do we think that it's going to go below 0? So just think about it for a little bit. If I tested some numbers here, I'm going to get some really, really small numbers and really, really big numbers, but none of them are ever going to go negative, and none of them are ever going to go to 0 even, actually. So our range is y is greater than 0. Not greater than or equal to, because it's never going to be 0. So that's the first thing I want to mention, is that the domain and range, domain is all real numbers, range is y is greater than 0. And then I want to show you something as well here with this tail end. Notice how as we get closer and closer and closer this way, or further and further this way, I mean, it gets closer and closer and closer and closer to this line here that I just drew in. That's actually called an asymptote. And before I find the equation for this asymptote, I have a section right here for you to write this down. So the equation of the asymptote, it's an equation of a line, and the graph I have approaches the line but never touches it. So it approaches the line but never touches it. Alright, and here we have to remember that a horizontal line has the equation y equals a number. How I remember that is that it's going through the y-axis, so it's going to be y equals whatever number it's going through. In this case, it's going through 0, so my asymptote is the equation of the line y equals 0. All right, so something that you may or may not have noticed is that when I'm doing a graph in general, let's write this equation down, y equals a times b to the x. It may already be on your sheet, but this number in front of the b to the x is going to be the y-intercept. And now actually this may not have been obvious, because if I go back to my original equation, it didn't have a value there. Really, it did. It was a 1. They just didn't write it. And that is why my y-intercept for this one is at 1. So the a value, or the number in front, is always a y-intercept, and if there's nothing there, it's a 1. And then the b basically tells us if it's going to be growth or decay. And also one thing you should know is that if a is negative, it's going to be flipped over the x-axis, but it's still considered a growth equation, which is kind of confusing. I'll say more in a minute, but if a is negative, the graph is flipped. Alright, so in general, here's how we're going to graph our y equals a times b to the x. We're going to first plot the y-intercept, then we're going to find another point, and really, you can find any point you want to. I just suggest that you use x equals 1 just because it's going to be the easiest. But really, you can find any other point you want to. After that, we're just going to draw in the general shape, and we're going to find the domain and range. That's it. All right. So when I did this form here, these didn't print very well. This one was supposed to be example 1, and here's what happened. It's going to be y equals 1/2 times 3 to the x. All right, step 1, find the y-intercept. Remember, the a value is the y-intercept. So my y-intercept right now is 0,1/2. Just do the best to graph it. And then step 2, find another point. Alright, so again, I could pick anything I want to, but I recommend using a 1 for x because it ends up being the easiest in most situations. So what that means is I take my equation and I'm going to put a 1 in for x. Use your calculator if you need to, but this ends up being 1/2 times 3, which is 3/2. So in my mind, I'm thinking 1.5. Alright, so I go ahead and graph that. And then step 3, draw in the general shape, because we know it's going to look like an exponential growth. And that's all you got to do for your graph. We also want to state the asymptote and the domain and range. So the asymptote in this situation, well, it has not shifted up or down. We'll be doing that later. So the asymptote has just stayed at y equals 0. And the domain and range are actually the same as we started with the one I did earlier. So the domain is all reals, and the range y is greater than 0. Alright, I want to next show you what it looks like if it's flipped over the x-axis. So for example 2, my equation is going to be y equals a negative 3/2 to the x power. Alright, step 1, find your y-intercept. And remember, if there's no number there, it's like a 1. In this situation, it's like a negative 1. So my y-intercept is at 0, negative 1. There it is, 0, negative 1. Alright, step 2, find another point. Again, you could find any point you want to. I recommend using 1 for x just because it makes it nice and easy. For example, right now, when I put 1 in for x, the answer just ends up being negative 3/2, and I didn't even have to use my calculator. So 1, negative 3/2. And you can see just naturally it's now going downwards, so it's going to go like this instead of up. And it seems weird, but that's still considered an exponential growth equation. It's just flipped over. Now this one, you can see the asymptote hasn't changed. So my asymptote is still at y equals 0. The domain is still all reals. but the range has now flipped. Because it's below the line, my range is going to be y is less than 0. Alright, I'm going to give you the equations for example 3 and 4, and I want you to pause and try to graph them, and then we'll check your work in a minute. So the example 3 was supposed to be y equals -2 times 2 to the x, and example 4 was supposed to be y equals 2/3 times 2 to the x. Alright, so pause the video and go ahead and try those two. Alright, if you have unpaused, we're going to really quickly check your answers. So for example 3, your graph should look something like this. My y-intercept is at 0, -2, and my other point is at 1, -4. And for example 4, my y-intercept is at 0, 2/3, and my other point is 1, 4/3. All right, and for those, asymptote, domain, and range are similar to what we did earlier, so I'm not going to say that again. I'm going to talk a little bit now about how to shift these graphs. So you maybe basically feel like you're an expert at shifting graphs now that we worked so hard on the square root and cube root graphs in chapter 7. And actually the equation for this is very similar as what we did in chapter 7. So just like I did in chapter 7, I have a general format I'm going to use, which in this situation is y equals a times b to the x, subtract h, and the subtract h is in the exponent, and then plus k is not in the exponent. And the nice thing is that the rules are the same as they were in chapter 7. So in the exponent here, if you see a plus sign, it's to the left. If you see a minus sign, it's to the right. So remember, it's the opposite of what you expect for that. Outside of the exponent, if you see a plus sign, it's up, and if you see a minus sign, it's down. And now to graph our shifted equations, we're going to first graph the quote parent function. There's not really a parent function for exponential though, it's just going to kind of be the format without the shifts. And then step 2, we're going to move our asymptote. In step 3, move the whole graph. So let me show you that on the other page. So pause and write those down if you need extra time, and then when you're done, flip it over. Alright, so here's 2 examples of shifting your graphs. First of all, let's identify what the shift is. So when I look at this, I see a minus sign in the power, so I'm thinking right 1, and then I see a minus sign outside, so I'm thinking down 4. And here's what I meant by graph the regular one. I'm going to first graph y equals 3 times 2 to the x, so no shift. And remember, think y-intercept, okay, so my y-intercept is at 3. To find the other point, I want to put a 1 in for x, and I have 3 times 2 to the first power. Okay, 2 to the first power is 2, times 3 is 6, so my other point is 1, 1, 2, 3, 4, 5, 6. And what I have just graphed right here is y equals 3 times 2 to the x without the shifts. So that is what I meant by step 1 on the previous page. So I just graphed the y equals a times b to the x without the shifts. And this step is optional. You are only graded on your final answer. So if you just want to put your final answer down, that's fine. Alright, so step 2 on the previous page, I had said move the asymptote. Remember that our asymptote is normally at y equals 0. So when I'm moving my graph down 4, my asymptote moves down 4. 1, 2, 3, 4. And I do want you to draw in your asymptote to get full credit for your graphs. So make sure you draw in your asymptotes. So that's my new asymptote. Y equals -4. And now what I'm going to do is I'm actually going to shift my points also, right 1, down 4, but that's going to be my guide for drawing in the shape of the graph. So each one of these I'm going to move right 1, down 1, 2, 3, 4, right 1, down 1, 2, 3, 4. But the reason I wanted this asymptote line in here is that shows me how far to go with my graph. And if you're missing that part of it, you are going to get points docked. Alright, the domain is still all reals. But if you look at the range, it has now shifted down 4, so I'm going to say y is greater than -4. That shifts with the asymptote. All right, tune in to part 2 to get the second example. Hey, welcome to 8.1 part 2. So we're just going to kind of continue where we left off at the top of the page here with this second translated graph. So I'm going to follow the same process we did with that first example. So, and again, pause the video if you want to try it on your own, and then you can check your work. But step 1, I'm going to graph it without the translations. So that would look like y equals 2 times 3 to the x this time. And it is very similar to what we just did, so be careful. But the y-intercept this time is at 2 instead of at 3. And then when I find my other point, I'm going to try plugging in a 1 for x, and I actually end up with 6 again. So 1 comma 6 is still the second point. 1, 2, 3, 4, 5, 6. All right, so that is my graph without the translations. So let's follow along and do step 2 next. So step 1, I graphed it. Step 2, I'm going to move my asymptote. Here's my asymptote originally. I am thinking when I look at this, I see a plus sign, so I'm thinking left 2. H is the opposite of what you expect. And then I'm thinking up 1 for the plus 1. So I'm going to move my asymptote up 1. So my new asymptote is at y equals 1. And then I'm going to move each of my points left 2, up 1. So left 1, 2, up 1, left 1, 2, up 1. And I've had my asymptote drawn in there as a guide so I know how far down the graph in the y area to put my little tail. So here's my answer. And for the domain and range, I am still thinking all real numbers for the domain. And the reason it's all real numbers, again, is because if I made the world's largest graph, my domain is telling me what x values would be used for the world's largest graph. So if I could do this to infinity, it's eventually going to cover all of the x values this way and all of the x values that way. That's why it's all real numbers. But for the range, it can never go below the asymptote. So the range is going to be y is greater than 1 because my asymptote's at 1 this time. All right, so that's graphing. Pause and finish that graph if you need to. Next, we're going to move on to the exponential growth formula and some interest formulas, which we're going to use with some real-world problems here. So let me tell you that a lot of situations you come across aren't as easy as y equals a times b to the x, and also we don't know what to put in for b. So I have a slightly expanded version of the y equals a times b to the x that we're going to use for an exponential growth situation, and here it is. It's y equals a, and then in parentheses a 1 plus r, and then outside of the parentheses the exponent is a t. And so a was the y-intercept, and if I made a graph it would still be the y-intercept, but for a real-world situation, that a is going to be the starting value, and that makes sense. It's kind of like the start of the graph. The r is going to be our growth factor, and this part in here is like b. Well, actually, you know what? I take it back. R is not the growth factor. This entire parentheses is the growth factor. So the whole parentheses is called the growth factor. R specifically is just the percent increase as a decimal. So let's write that down. So R is actually the percent increase as a decimal. And just a quick reminder, random, if I had 45% as a decimal, remember, move the decimal point 2 places to the left. Okay, ask me more about that in class if needed. And then last but not least, I got the t value. That's going to be the years since the start happened. And by the way, it's not always years, but about 90% of the time it is going to be the years. So that's why I want to say that. So the years since the start is t. All right, let's do an example of this. In January of 1993, there was 1,313,000 internet hosts. During the next 5 years, the number of hosts increased by 100% per year. All right, so here I have my starting amount. Here I have my percent increase. I have my starting date, and then it tells me during the next 5 years. We don't know yet if we're actually going to use that information or not. That might just be there to tell us for how long the model is valid. All right, step A, I want to write a model, and it says given H in millions, and then T is the years past 1993. When they say in millions like that, what they mean is they want you to translate your number into millions. So there's 1 million, and then 313,000 would be represented by 0.313. And then I could say million. So that's that translated. All right, so that is going to be my A value. It tells me to use H instead of Y, because H is going to be represented by the hosts. So I'm going to say Y equals 1.313. All right, in the formula I have a 1. And then I have to put in right here R. So R is my percentage as a decimal. So in my mind I'm thinking move my decimal 2 places to the left. So it's going to be 1.0, so just 1. And when I am making a model, leave T as T. So I don't want to fill in anything for that yet. I want to leave T as T. So my final model looks like this. Actually, you know what? I said we're going to use H, and then I didn't even write it down. So it's supposed to be H equals 1.313, and then 1 plus 1 is 2. All right, there we go. So that is my model. Part B asks, how many hosts were there in 1996? So actually, they're really asking us to use our model, and they told me 1996, so I got to figure out what T is. And in my mind, I am thinking 1996 is 3 years past 1993. So in my mind, I'm thinking, okay, T is 3. Let's fill this into the formula. I got 1.313 times 2 to the 3rd power. When you're doing an exponential equation like this, according to order of operations, exponents always comes first. So if I'm going to do this by hand, I would do 2 cubed first, which is 8, then multiply them. If you're using a graphing calculator, most of them can do that without a problem. But if I round it, I end up with 10.5. So 10.5 million is the answer. All right, step C asks us to graph the model, but I'm going to read ahead a second and see that step D wants us to use the graph to estimate the year when there was 30 million hosts. And remember how I said the H or hosts was the Y value? That means I'm going to want the Y values to go up to 30. So when I'm thinking about labeling my graph here, instead of going 1, 2, 3, 4, 5 like I maybe normally would, I want it to go up to 30. So I'm going to label it by 5s. So I'm going 0, 5, 10, 15, 20, 25, 30. And when I'm graphing this, that is again representing how many hosts in millions. How many hosts in millions? And then my other variable, the X variable, is representing the time. So I'm going to say that is the time in years. Now, normally you just have to graph 2 points, but in order to actually do part D, which is estimating, we need to be a little bit more exact here. So what I'm going to do is create a table of values, and we'll just find the first several just to make sure that we have a nice graph, a nice enough graph that I can do some estimating. When X is 0, that is the y-intercept actually, so that one's just 1.313. And go ahead and fill in the rest every time I'm just plugging in these other values for X, and I'm assuming you guys kind of know how to do that, so I'm just going to skip ahead and give you the answers. So when I put a 2 in for X, it's 5.252. When I put a 3 in for X, 10.504. When I put in a 4 for X, 21.008. And I'm going to just do my best to graph that. And so 0, 1.313, 1, 2.626, 2, 5.252, 3, 10.504. Again, just do your best. Okay, 4, 21.008. There's my model. And see how we can get a much more exact model because we used more points. All right. And now I can do part, oh, and one thing I should say, this is a real-world situation. You can't have a negative time. So we're not going to go below 0 this time because we can't have negative years in this situation. or in any real world situation, you can't have negative years. So when you're doing a real world graph, you will always start at 0. All right, part D. Use a graph to estimate the year when there were 30 million hosts. That's my Y value. So I'm going to kind of draw in a line if you need to kind of help yourself, but I'm looking for that spot. So let's just kind of scroll down. It looks like it's at approximately 4.75, and that's a guesstimate, but that's the best we got. So I'm going to guesstimate 4.75 years. So what year were there 30 million hosts? Well, I started in 1993, so this is about 1997, but almost to 1998. So maybe it's like September of 1997 or something like that, but that answer is sufficient. The last thing we're going to do for section 8.1 is do a similar type of problem, only now instead of just a regular exponential growth formula, we have translated it to represent compound interest. And this has a new formula. Here it is, and I'll explain what each of these things mean in a second, but it's A equals P, and then in parentheses 1 plus R over N, and then N times T is the exponent. So P, and then in parentheses 1 plus R over N times T is the exponent. All right, this time the P, it's actually a P because it stands for principal, but that's still the starting amount, so still like A value or the y-intercept if you're going to graph it, same thing. R is still the rate as a decimal. I'm going to erase some of this stuff so I have more space. All right, so R is the rate as a decimal. And T is still the time. And in this situation, it's not always years, but also I'll just say time right now. And then we got this new variable, N. N is how many times interest is compounded per year. All right, and then A stands for the ending amount. All right, so what I mean by N is how many times it's compounded by year. You guys may or may not have known this, but interest is not always compounded once a year. Interest is compounded more than once a year. So sometimes interest is compounded annually, which is once per year, so we'll say N is 1. Could be quarterly, which is 4 times per year, so N is 4. It could be weekly, which is 52 times per year, because there's 52 weeks. It could be monthly, so 12 times per year, or it could be daily, so 365. So when I'm going to do this next example here, it has the same starting amount, and the same R, change it to a decimal, every time, and actually it told me after 1 year, so T is going to be 1, but N is going to change every single time. So let me show you how this formula is used. I'm going to plug in my P value, which is 1,000. I'm going to plug in my interest rate as a decimal. N is 1 this time, and then N is 1, T is 1. When you type that into your calculator, you end up with $1,080. All right, so let me show you quarterly because it looks a little bit different when you do that with a number besides 1 right here and here. Okay, so I still have a principal amount of 1,000. Now the rate is still 0.08, and notice I'm just plugging things into the formula, so I'm not doing anything fancy right now. All right, a few things to comment on. If you're going to use your calculator, make sure those go together. I would recommend, well, you know what, honestly, if you have a graphing calculator, you can just type it all in. Sometimes students don't have a graphing calculator, so I'd recommend do this part first, figure out what that is, and then times by 1,000. Your choice, though. You should end up with 1,082.43. All right, try the rest, and then check your answers. I'm going to write them down quick before I run out of time. So here's what you should have for the other ones. go ahead and try those, and then we'll say more in class. Thanks for listening. Talk to you soon.